Hi, this is a video for compiler design, Comp 442 and 6421. In this video, I'm going to present assignment number 2, which is about syntactical analysis or parsing. So let's see where first we find this assignment handout. Here under week 4, I have handout. If you click there, you're going to find a zip file that contains this content here. This is a PDF describing the assignment, which I'm going to go over in this video. Here is the grammar. This is the main input, I would say, of this assignment. So this is the grammar that you will have to change into an LL1 grammar first, and then implement using a top-down parser. There are only two kinds of parser you're allowed to use, either a recursive descent predictive parser or a table-driven predictive parser, which I have already explained in the lecture in week number 4. We are going to continue explaining this, particularly in week number 5. I'm going to explain how to do the error recovery with predictive parsing. These are the two main examples that I'm giving you. So these are two complete programs. One is using classes, one is not. These are exactly the same examples that I gave in the handout for assignment number 1. Here, this is a jar file, which is a tool that I wrote myself that I propose that you use to help you transform the grammar. This tool, what it can do is, well, if we can see on the blackboard behind me, let's stop the share here. So that's essentially the procedure that you have to do in order to do this assignment. So first of all, you have to study the grammar. So you're gonna live with this language for the rest of the semester, but it's very important that you study carefully what this language is all about. So you have classes, which includes data members and member functions, which are only declared inside of the classes, which are then implemented outside of the classes. A little bit like C++ would do it. So you don't have, for example, functions that are implemented inside of the class declarations. So it's essentially a variation of languages like C++ or Java. So first, study the grammar to make sure that you understand what is the actual structure of the language that you are using. The reason why it's important to study the grammar, it's important to be first aware of what is it that you need to change in the grammar. You can't use the grammar as it is, as I'm giving it to you in the file, and the GRM file. Because this grammar that is there is in no way a LL1 grammar, which is the kind of grammar that you need to have in order to implement a predictive parser. Essentially, you have to apply some transformations to the grammar, which I have explained in week number 3, during week number 3 in the class. So studying the grammar, very important as a start. Make sure you understand what is this language that we are using. Second, you should use the grammar tool, which is the tool that you have in the jar file that you have in the assignment handout. This tool can help you to remove the EBNF optionality. It also can help you to remove the EBNF repetition. It also can help you remove the left recursions. So that's 3 things that I've shown in week number 3 as to how to remove a transformation that you can apply to remove each of these things if they are in your grammar, which our grammar does have. So you use this tool to actually remove these things from the grammar. So all you have to do is to take this file and feed it to the tool. there is a usage that is explanations that are given in the README file, okay, in the handout. So essentially, you feed the grammar to this tool, and then it's going to write out a file into an output file, which is going to be another grammar to the same language, but that will have been transformed. You will right away see that, of course, when you apply transformations to a grammar, you have to add non-terminals, you have to change how the rules are being expressed. And then you're going to quickly see that this grammar does not look as clear as it used to be in the handout. Okay, so that's why it's very important that every step of the way you look as to what the grammar has now become after these transformations, so that you somehow still understand the structure of the grammar. Okay. Because this tool that I'm giving you, it cannot locate ambiguities or remove the ambiguities. There are some other tools that you can use to locate and remove ambiguities, namely A2CC or the website that is developed following the A2CC tool. Please go to the lab instructors during the labs. They are there to teach you how to use A2CC or the corresponding website. There's also a website from the University of Calgary that you can actually use to achieve the same goal. It's not the same tool, it works differently, but it can enable you to actually locate ambiguities. It does not. The University of Calgary provides you with some ways to actually, well, first, it does enable you to locate the ambiguities. That's not a problem. But removing or transforming the grammar to remove the ambiguities is the main problem here. Some of the ambiguities can be removed using factorization. Some other ambiguities have to be removed by somehow re-expressing the grammar in a different way so as to remove the ambiguities. University of Calgary provides you with some transformations that can be applied, but don't expect that you're just going to press a button and that's going to be magical and that's going to remove everything. In fact, this step number 3 here, as I posted here on the board, this is the most tedious part of the entire assignment. So please don't underestimate, in particular, the work involved in this third part. So as you may see, this is the assignment for which I give the most time to solve the assignment. There's a reason for it. It's actually the assignment that takes the most time, and the most time to do this assignment is very often this step here, how to remove the ambiguities. It is very tedious, very confusing, very error-prone. So please don't underestimate the time and level of difficulty of this part number 3. In fact, after you have successfully transformed the grammar, implementing the parser, it's not that difficult nor very long. Okay, so the most difficult part of the entire assignment is actually this part here. Okay. So once you will have actually transformed your grammar, then what you will need to do is to generate the first and follow sets for this grammar. As I explained in class, you need to have the first and follow sets. Any of these tools will actually be able to give you the first and follow sets of any grammar that you give to it. So the grammar that you have transformed, you actually find the first and follow sets for it, and then this enables you to generate the top-down parser that corresponds to this grammar. So you can do either a recursive descent parser or do a table-driven parser. If you choose to do a table-driven parser, then you can actually use the University of Calgary tool to construct the table. So you just give it your grammar, and then it will construct a table, which is going to be given to you on the browser. So it's just a question of taking this table that is presented to you on the browser, and copy paste it into somehow your program and incorporate this table into your program in a way that your program can actually read it. And then build the parser that is following the information that is presented in this table. So I have explained extensively in class what are the advantages and drawbacks of either recursive descent or table-driven parser. So I'm assuming that you are aware of that. Okay, so let's go back to this. Let's go to the assignment handout. Okay. So that's the handout. First, it's due on February 19th. So the job here that you have to do is to build a parser. Here, this is a description, formal description of what is the grammar. These are all your non-terminal symbols in this grammar. These are all the terminal symbols in this grammar. Of course, here, the terminal symbols of the grammar, they correspond almost one-to-one to the tokens that you have identified using your scanner, your lexical analyzer. So each of the things in the list here should correspond to one of the kinds of tokens that you have already identified. So when you see in your grammar, when you see these terminal symbols, then they correspond to tokens that you have identified in your assignment number 1. So these are the rules of the grammar. Notably, if you have double squiggly brackets like this, that actually represents EBNF repetition. Okay, so that means here a list of class declaration or function definition. If you have double square brackets, such as here, then that actually represents EBNF optionality. Okay, so essentially here, this whole thing here can be there or can not be there. Essentially here, this is the list of classes that are inherited by a class that you declare, the inheritance list of a class. And so on and so forth. So you have other things like, for example, here, you have other things that are repeated, like ID nest here is also repeated. Indice is also repeated here. So you see that you would have to remove each of these by doing a transformation of the grammar. The tool that I give you, the jar file, is actually enabling you to automatically remove these. So I invite you to use the tool and then to actually look at the result of the transformation and somehow acquaint yourself with the transformed grammar. You will quickly see that the grammar does not look as clear as this grammar is actually. This grammar here that I'm providing to you, I made it so that it's as clear as possible. What is the language that we are parsing? Once you will apply the transformations, you will start to see that it does not look that much clearer anymore. So that's why it's not going to be so evident to actually apply the transformations, because it's not very clear what grammar you are working with anymore. Okay, that's why it's important each step of the way that you try to make yourself acquainted with the grammar that you now have. Of course, when you have to build the parser, then you will have to be familiar with the transform grammar. So very important that you study the initial grammar and we apply transformations, that you reacquaint yourself with the transformed grammar every step of the way. Okay, so that's the grammar. So in this grammar here, of course, the things that are in an angle brackets like this are the non-terminal symbols, and anything that is in single quotes is the terminal symbols or the tokens that you have identified by your lexical analyzer. There are some epsilon rules in this grammar, and they are represented using this here, epsilon. EBNF repetition is using double squiggly brackets, and EBNF optionality is represented using square brackets. That's about it. Okay, so first, well, here this is basically the steps that you have to do. There's also things that you need to submit. So what is it you need to submit? First, your transformed grammar that has been transformed into LL1. You need to provide to the marker the transformed grammar. Then the first and follow sets of this grammar. I explained to you how to generate the first and follow sets. Please use tools to actually generate the first and follow sets, as it should have been evident as explained in the class. It's very tedious to design first and follow sets, especially the follow set. So please use a tool to actually generate them. Some people think, oh, he doesn't want us to use compiler generation tools. What I don't want you to use is a parser generator. You can use tools to do some of the transformations, generate the first and follow sets, generate the table for the parser. So I am allowing you to use some tools. And then third, little description, brief description of your design, and then a description of what are the tools that you use to along the way to actually solve the problem. Like, for example, if you use A2CC or the University of Calgary tool, especially the University of Calgary, it has many different tools. So what tool in particular did you use for what purpose? And hopefully explain why you actually use this tool as opposed to another tool that you could have used. So here I'm asking you to explain your usage of tools, because it's an important skill to be able to know what tool to use and for what reason for a certain purpose. For the implementation, of course, what you need to implement here is the parser. So this should be done according to what I have explained in class as to, depending if you're implementing a recursive descent predictive parser or a table-driven predictive parser. And the parser should be implemented according, of course, to the transformed grammar that you are providing. One thing is that the parser should read a program. For example, one of the two programs that I'm providing you here in the handout, the bubble sort or the polynomial program, are two example programs. Like, for example, bubble sort is this one here, which I already shown in class before. So you should be able to read from this extracted tokens. Of course, what is reading from the file should still be your lexical analyzer. And your lexical analyzer reads from the file, and when you call next token, it should extract the next token from the file and then return this token to the parser. So the parser will call your lexical analyzer's next token function to receive the next token from the file. The parser should not read itself from the file. It should only call the next token function that you wrote in assignment number 1 to get the next token. So it reads from a file, and there are two outputs that there should be for the moment. First, I'm asking you to output a derivation. So I've explained what is a derivation in class, and especially in week number 4, I have explained, when I have explained the table-driven parser in the last column, in the final example of week number 4's slides, you see that there's a derivation that is being constructed as the parse is going. So this is this exact kind of thing that I actually want to have in the out derivation file. So let's have a look at it. You see here, when the parse is happening, I'm showing here how you can actually construct a derivation every step of the way. Of course, here it is showing how it would, how it would be happening if you're building a table-driven predictive parser. But as I explained in class, even though it seems that it's very different how the regressive descent predictive parser and the table-driven predictive parser are working, once you understand what they're doing, then you realize that they're doing both exactly the same thing, even though one is using a stack and the other one is using hard-coded functions. It seems very different, but it's actually the same. So I'm saying that every step of the way, even if you're using a regressive descent predictive parser, every step of the way of the parsing, you can actually construct a derivation like this. Okay. So every step of the way of the parsing, I want you to output to a file a derivation. So first you read, you write one line, that is the first line here, which is the obvious one, is the starting symbol. And then essentially you transform this starting symbol into a sentential form. And then every step of the way, the sentential form is transformed into another sentential form by using some rules. And then so on and so forth until you come at the end where the last line of the derivation is the actual program that you were parsing, which constitutes a proof that you have transformed the starting symbol into the program itself. So it's a proof that this program can be derived by the grammar. Okay. So I want you to output to a file the output to a file named out derivation, .out derivation. So if the original file was called original file name, then you should have a file that is being generated, original file name .out derivation. So the original source file was, let's say, original file name .src. Then the output file should be original file name .out derivation. That's one file I want you to generate. Eventually, you're going to find syntax errors, which we will talk about in week 5. I want you to output the syntax errors into a file named original file name .out syntax errors. Okay. So every step of the way, when you find errors, you will output them to a separate file. Why do I ask you to output a derivation? Because it is very helpful if something goes wrong with your parser, then you can look at the derivation file and then see where it actually stopped. Okay. Assuming that you output the derivation to the file every step of the way, of course. So most of the things that I'm asking you to do, the output files I'm asking you to write, are actually, I ask you to do them because they're helpful to you as a debugging tool. Okay, so derivation output, error reporting output. You must also do error recovery. we will talk about this in week number 5. There is a simple, not simplistic, but simple way to do error recovery, which I will explain and which you can easily introduce in your parser. So error recovery is part of assignment number 2. You must also provide your own test cases. The 2 files that I've given you, they include many of the things, but they don't include everything. So I'm expecting that you will have more test cases that will include the things that are not included in the 2 files that I'm giving you. For example, for every, let me see the bubble sort. So if you see at the end here, I created a list of all the things that could be present in a program. And you see that I have put up check marks here. And there are many things for this particular program that don't have check marks. Essentially, what you want to achieve is that collectively, all your test cases have at least one check mark in every of the things that I have listed here. Okay. If you check my 2 examples, you will see that some of these things don't have check marks for neither of my 2 examples. So then I would be assuming that you would have other examples that do have check marks for the things that are not in my examples. All this to say that it's actually quite tedious and difficult to do complete testing of a compiler, because there's many different combinations of things that you could have together and so on. So testing a compiler it's a difficult task, because there are so many different kinds of programs that you can write. Okay. So PDF, let's go back to the PDF. And then, of course, you should provide a driver so that the marker can actually execute your parser easily. The best thing would be that the driver is actually calling the parser for every of the files that you have in input, and that it would actually, of course, generate the files, the output files for all of the input files that you give to the parser, so that the marker doesn't have to repeat the testing manually for every of your test cases. It's possible that you will have many, many test cases. So probably you want your driver to actually call the parser for every of your test cases in one, batch. So all this to say that it's necessary that we have a driver that exercises the parser without having to do it manually. So that's about it for that. There is the grading scheme here. You will have a much more detailed grading scheme available about 1 week before the deadline, the due date of the assignment. Just like I gave you the detailed grading sheet for assignment number 1, you'll have a similar, conceptually similar grading sheet available for assignment 2 and all the other assignments. So that's about it for that. Thank you. Bye-bye.